Hello and welcome to our first session of our latest workshop series, Simulation for Makers. First of all, guys, sorry for the confusion and that you had to wait some time. We had some technical problems with GoToWebinar and therefore decided to wait until everybody is able to join the session. Right, and just before we actually start to dive in our today's webinar, I would really like to make sure that everybody can hear me. So guys, there is a button which you can find on the in your GoToWebinar app, which is called Raise Your Hand. And with this button, you can virtually raise your hand so that I can see that there's a problem or a question or something else. And therefore, please press this Raise Your Hand button in the case you can hear me, so that I know that everything is fine. And great, I see some first hands. And if something should happen during the session and the audio quality is not good anymore, you can also use our free toll-free audio service numbers. These numbers you can see here, you can just call them, it's without any cost for you, and then you just have to enter this access code for the session, which is 816-119-637 to join the session, or to then join the audio of the session using your phone. Okay, great, then I think we can start to dive into our today's webinar. And first of all, let's just figure out what you can expect from this workshop series or from this session. In the very beginning, I will tell you some basic facts about our workshop and this webinar. So what is the idea? I will also talk about your opportunity to win a free professional training and introduce a little bit our company. Then we will talk about the fundamentals of simulation. So you will get a very hands-on introduction to what is engineering simulation, what is the standard process, and how can it help me as a maker to optimize my product or my ideas. After that, you will get your first live demonstration on SimScale. We will discuss the results of the simulation. After that, I will present the homework to you, and we will have a lot of time for your questions and my answers. Great, so if you have any questions, by the way, just type it into the question dialog box of GoToWebinar, and I will try to answer them as soon as I can and latest during the Q&A session. Okay, let's start to talk about our today's webinar. First of all, I would like to introduce myself. Maybe some of you know me already. My name is Milad. I'm working at SimScale as a marketing program manager. And yes, we at SimScale will really try to create the next big thing for engineering simulation. And my job there is to make sure that SimScale becomes the one and only place for engineering simulation in the future. And one part of this job is to deliver and organize webinars and workshops with you guys to teach you the new and latest stuff about engineering simulation, how to use it for your own projects. By the way, I have a mechanical engineering background, so I get used to simulation in the very early stage of my career. And the idea of this workshop today is that there are a lot of very enthusiastic and engaged makers and hobbyists out here, and we would like to show you how you can use our platform, which is for free, by the way, to optimize your own ideas and products. So you will gain a lot of very interesting and hands-on insights about engineering simulation, and you will also learn how to use the simulation yourself. And since this is really hands-on and focused on makers, there are some things we cannot deliver. And one point is that we will not be able to talk so much about theory or fundamentals of simulation. That means we will not talk about mathematical algorithms or the real basic physics behind this, just because it will take so much time. If you're interested in that, I would really say you should read one of the great books about this, which is available, or if you're a student, I'm quite sure there will be also a course at your university about numerical engineering. And if you're more interested in a, let's say, a commercial or industrial application of engineering simulation, this training also maybe is not perfect, or the webinar is not perfectly ideal for you. But the good news is, Joining this training and submitting all 3 homework will qualify you for a free professional training with a value of €500. And last but not least, we would love to get your product feedbacks and contributions. So whenever you have a question, please reach out to me or to my colleagues, and we would really love to see very soon your own simulations in our public simulation library. Okay, then let's talk more about this workshop and the homework. So after every session, you will have the chance to work on an optional homework assignment. This homework assignment will help you to deepen the knowledge which you gained during the webinar. And we will also provide a step-by-step tutorial, which is very detailed. It will help you to do the homework and to submit it. And you have 1 week after every session to work or to do the homework. And if you submit all these 3 homeworks, you will get automatically a certification of participation and access to a free workshop. And just because I got a lot of questions, I would like to discuss the, let's say, most relevant or most frequently asked of them right now. So this workshop will be recorded, and we will publish the record as soon as possible on our website and on our YouTube channel, simscale.com/makerworkshop. And please don't start to simulate during the webinars themselves. The focus here should really be that you should try to understand everything we're discussing and ask your questions. And after the webinars, you have more than enough time to do the homework assignments or simulate something yourself. If you need support, we have a public forum section, our SimScale forum, where you can post your project, ask questions, and you will get the help as soon as possible by my colleagues or by some other users. Okay, and last but not least, whenever you have a question, don't be shy. You can reach me directly at mmayfie@simscale.com. Okay, and since you guys joined the session to learn something about simulation, I would suggest to start right now with the fundamentals of simulation. And maybe because there are some guys here who never worked with simulation, I would try to explain you what engineering simulation is and for what it is used. Basically, engineering simulation describes technologies, or let's say more software in the most cases, which is able to replace a physical experiment by a computation. So instead of building a model and putting it into a wind tunnel, we will just simulate the flow around the car, calculate how the flow should act. And it's the same we can also do instead of a real crash test, a virtual crash test. And all this is engineering simulation. And to understand why engineering simulation is so important today, let's take a look at the standard product development process. Just imagine you are working as a design engineer in a company which is producing valves. And your boss says, well, we need a new valve. And first of all, with a conventional design process, you would start to design the whole valve, which not only includes, let's say, the gate of the valve. I mean, this is the main responsibility of a valve, to open or to close a pipe. It also includes all auxiliary parts, like all sealings, all screws, also the electronics. And once you finish the design and spend it so many hours on this, you are able to produce a prototype. So you're manufacturing your design, you can test it, and then change the design and reduce the cycle again and again. This cycle is not very productive or efficient because you're spending a lot of energy and time at the very early stage of the product without optimizing let's say, the key feature of a product. And therefore, simulation can be used to really push and increase the speed of this design processes. So you also start with designing, but instead of designing the whole valve, for example, you can just design, let's say, the most important structure of the valve, and first of all optimize the flow through this valve. And you don't need to manufacture anything. It's much cheaper and allows you to create and design your products better in a faster time and with less money which you need to spend. And maybe a lot of you will ask, if simulation is something so good, why is not everybody using it, or why is it the first time I hear about it? The question is, or the answer is quite easy. Simulation traditionally was very expensive. There were like three barriers which were making it very hard for small companies and single users to adapt this technology for their own company. Because traditionally, for simulation, you need dedicated software licenses, specialized hardware, and people who are able to operate both the backend as well as the software. And here we come with SimScale, which is a very or completely new approach towards engineering simulation. SimScale is the first web-based engineering platform. That means you have no installation, no licenses, and you even don't need your local computing power because everything is done in the cloud. You can access SimScale from your web browser. You just need a standard web browser internet connection and can access our full 3D work environment to create yourself leading edge or cutting edge simulation. Here you just can see some examples. So this is SimScale running in your web browser, and you can see some simulation which were performed with SimScale, starting from a harmonic analysis of an umbrella, particle simulation in a mill. Here you can see the valve we talked about, the flow through the valve, but we also have thermostructural simulation like the simulation of this gearbox, or even aerodynamics of a racing car. Additionally to that, SimScale also brings together content and people. That means SimScale is the biggest community there about engineering simulation. And so you can not only use SimScale, which is, by the way, in our community plan for free, but you can also interact with other people, find new friends, and get help. And as I mentioned, we have a very strong community, which I would like to introduce to you very quickly. So maybe in the next weeks, the most important part of SimScale will be the forum. Let's just take a look at the forum. This is the SimScale homepage, simscale.com. And on the community, you can see here the forum. And in this forum, we have a lot of categories. For example, this project spotlight, every public simulation project got its own topic. And we also have a SimScale Workshops category, and here you can find the Makers Workshop. And if you have a question, for example, regarding the homework of the first session, you can just write it here in the forum. But beside of this forum, we also have public projects we talked about. Just to make it clear, public projects or public project library is really a place where you can find thousands of ready-to-use simulation projects, and you just have to open them, and then you can import them to your own SimScale account, modify them, or do with them whatever you want. And so it's a huge source of inspiration for you, which will also enable you to learn very quickly by adapting existing simulation templates to your own problem. We're also offering workshops as part of our community, like the Maker Workshop we're starting today. And we also have, I think, what is very important, if you want to learn more besides the workshops, you also have a lot of stuff for learning and documentation. So if you go on help, you can access our documentation here. It's HTML documentation, so you can just look for keywords. And you can also access one of our video tutorials, which we have for different, let's say, different problems or different parts of our tool. Okay, then I would like to start with a live demo. And first of all, let's talk about what we're going to do today. And this is, I think, a very good example for makers. This is a CAD design, a CAD model of self-designed 3D printable mini drone, mini quadcopter drone, which has, I don't know, maybe the size of a small lunchbox, so it's a very small vehicle. And you have like 4 electrical engines with propellers, which are generating the lift force, so that the drone can fly. And these engines are connected with 3D printed arms to the mainframe. And you can imagine this is, in the end, should be as light as possible and as strong as necessary. Because if it's too strong, it means it has a higher weight, and therefore it will decrease the performance, the flight performance of the drone. And we will right now try to answer the question if this design is suitable for the drone. And in the end, what will happen, what we know is that this left side is fixed, so it cannot move. And here we have a lift force, which is normal to the surface. So what we know in the end about this whole model is the geometry, material properties, and loads and fixations. And what we don't know and would like to find out is the stress and displacement distribution within the whole part. And let's talk right now about the general simulation process. So what we will do is, first of all, we have to do the so-called pre-processing. Pre-processing means that we are preparing the CAD model, our design model, to use it in SimScale for preparing a simulation. So we have to import the CAD model using a neutral file format, and then we come to a very important point called meshing. And it only means that you have to divide your existing model into small tetrahedral or hexahedral elements. And these elements are later on like a mesh. That's the reason why we call it mesh. You can see it here in the middle image a little bit. And for every node of this mesh, displacement, etc., and stress are calculated, and not between these points. And when in the end, this step is important because you have to define which accuracy, with local accuracy, you want within your model. Then you have to set up the simulation, like tell the SimScale what part of the model should be fixed, what part, on which part you would like to apply a force, and when the computation is done, you can animate and visualize your results online. Okay, then let's start. I've prepared something. First of all, here. This is a project which only contains a CAD model, and let's open this project right now. And here it is. So sometimes it takes a little bit more time, sorry for that. And here we go. This is now SimScale. Here you can see our three-dimensional geometry of the drone arm. And first of all, let's just do some general checks, like checking the bounding box diagonal length of 10 centimeters, which makes sense. We have one solid in total and 123 faces, so the model seems to be closed and everything is okay. And now we will create the mesh. Therefore, click please on this mesh item on the left side in the project tree. And then it will open a new menu in the middle where you can see available mesh. And since we have not created any mesh, this list is empty. So let's first of all click on Create New Mesh. And then this will create a new mesh object. First of all, we can keep the name and we have to select the base. And the base in our case is the model, because we want to mesh this CAD model, this drone arm. So we'll choose drone arm, click the Save button and confirm that we want to switch or assign the base. Next step is to click on the Add Mesh Operation button. And here you can choose between different mesh algorithms or mesh tools. We will use T-Tree with local refinements. And what we have to do right now is first of all to define, let's say, a general mesh size. So it's more a range, like what should be the maximum and the minimum edge size of our mesh, etc. And then later we can also define refinements. But this is so like the overall maximum refinement range for parts which are not refined. And here we will start with 1 millimeter to 6/10 of a millimeter. We'll make a first order mesh. What this means will be discussed just in 1 second. Coarse is enough, and 4 cores are also enough. So we will use 4 processors to calculate the mesh. click the Save button, and then we will add a mesh refinement. And we need to add the refinement everywhere where we expect higher stress. So I think here we can expect a little bit higher stress, and here too. Just faces, add selection, and now we can define the element size range for this refined part. And now we're basically done, and we just have to start the meshing process with clicking this button. Okay, and that's it. Now we just have to wait several minutes until our mesh is computed. So let's do a quick wrap up what we've talked about. I showed you how to open a project, which was the project including the arm, and then we created a tetrahedral mesh with refinements. First of all, we checked if the geometry is fine. Then we added a new mesh object, and then we choose the general mesh, let's say a mesh fineness range, the order of the mesh, and added a manual mesh refinement. There are some advanced topics we cannot talk about today, as I mentioned. First of all, CAD cleaning and repair, because in most cases you don't have such a nice CAD model. You have to close gaps, make it watertight, and sometimes also defeature it or simplify it. And I mean, this is a kind of manual meshing, but in the end you can also do a lot of more manual refinements using tetrahedral mesh. Okay, now before we resume with the next step, by the way, here you can see our mesh generation is already finished. Let's just take a quick look at that. And then we will just talk about first and second order meshes. And here is our mesh, and here you can see the refinement. Okay, here you can see an option, first or second order. What does it mean? Let's talk about it. In the end, it's quite easy to understand. Just imagine you have a curve. This could be, for example, a mathematical function, which is looking like this. And then it's basically two possibilities. One of them is, if you would like now to, let's say, have a numerical representation of this infinite curve, we can do this meshing, and first of all divide this curve into points. And this is in the end what the mesh is doing, or the mesher is doing. And now, in the end, when we talk about first order, it means that we are using for the interpolation with this point linear interpolations. That reason why first, which is in the end like this. You have lines between the points, straight lines. Yes, and that means that in the points you are very exact, but between the points sometimes you can have a big difference, like here. And another option is to use second order elements. And second order elements are using a second order function instead of like a spline, instead of a single line to connect the points. And that allows you with the same number of points to achieve much higher accuracy. On the other hand, you need much more computational power to generate second-order meshes, and sometimes it fails. So therefore, I can really recommend you to use, first of all, only first-order elements. Great, we're now ready for the next step. After our mesh is created, we go to the simulation designer. Here we can create a new simulation. And then you can choose, first of all, what you want to simulate. In our case, we will do solid mechanics and static analysis. Just click on Save. And now here on the left side, you can see this, let's call it project tree, which will guide you through the whole simulation. First of all, we have to choose which mesh is the base of our simulation. We will choose this mesh 1, which will be added then to the 3D viewer. And then the first thing we have to do is to define the material this part is made of. Some of these elements here or sections are optional, so everything which is mandatory has this red bubble, and you cannot start the simulation until everything is green or at least blue. So let's start to add a material, and you can for sure choose from our material library. And we will use in this case the first material, ABS, which is the standard plastic for 3D printing. We just have to select the volume we want to apply this material model on, and we can do it with this list or also graphically by changing the selection mode, pick volumes, select it, and then save. And now this becomes green. And then the next step, we have to fix one side. So let's call it fix here. Choose this surface and this surface. And this means that all nodes on this face cannot move either in X, Y, or Z direction. If I would choose this to unconstraint, then it could move only in that direction. So like this, in this direction of the Z-axis. We can save, and next we just have to add a load. For this, create a new load boundary condition, and the type is a nodal load. We will choose the surface and add 0.75 Newton in Y direction. And here you see maybe one problem. You can only select a node. And so if you don't have a node like here, a selectable node, you could even not create this boundary condition. And therefore, you can just change your analysis type to advanced. Then you unfortunately have to reassign everything you've selected so far. But the big advantage is that right now it's easier for you to define your boundary condition. And this is something you should really keep in mind. Think before you start to design your simulation what you in the end want to do. And in here it's the same like last time, so we just have to select these two faces, and it's done. And we again create a load boundary condition, but instead of pressure we can now choose force, choose the surface, again 0.75 Newton, and then we're basically done. Now we don't have to touch numerics because the default values are fine, and we also don't have to touch this, it's fine. What we could do right now is to add additional solution fields. Right now we have displacement, Cauchy, von Mises stress, and total strain. And you could, for example, also add nodal forces if we're interested in them. Then we just have to check the simulation, create a new run, and start it like that. The calculation is now done remotely on our high-performance cloud infrastructure, and you will be noticed as soon as the simulation results available. And let's maybe now do, first of all, a quick wrap-up, what I've showed you. So first of all, we talked about general setup, so you have to switch to Simulation Designer, create a new simulation, and choose the type of simulation you want to run. Very important, please think before you start to design a simulation what kind of simulation you exactly want, otherwise you have to do some work maybe twice. Then I showed you how to assign a mesh. This also contains how to define a material model. You can import them from a library or based on your own parameters, and how to apply this material model. And finally, we talked about boundary conditions and start the simulation. There are some advanced topics we cannot cover today, but which we'll cover during the next week. Then we will talk about context, which means, or which are necessary if you have more than one solid body in your physical system. We will talk about numerical solver settings and a little bit also about advanced solver controls. So the simulation is finished. It took like 1 minute to calculate. And now we can switch to the post-processor here. And click on Solution field. That sometimes take a minute. But don't worry. I already see some questions. Guys, don't worry, I will answer them just after this live demonstration. And here we go. So our live 3D post-processor is initialized. And now we can start to play around with the results. So first of all, what you should consider. This, or the simulation result, is nothing more or less than a very big table with a lot of numbers. So you have, like, for every point of the mesh, you have a list including the force, the strain, the stress, and the displacement there. Now we can use our online post-processor tool to visualize this information. And first of all, what we can see here is the von Mises stress distribution. Let's open the legend. And then you can see that, I think what we expected, that you have a lot of high stress regions here because of the thin structure and the long leverage arm. And we can also take, so the maximum stress is like 6.6 E plus 5 Pascal. Very important. We're using SI units here, so it's Pascal, not megapascal. And we can also, for example, if we want to know the displacement, we can use this wrap by vector filter. Use the displacement vector. And now it takes maybe 1 or 2 seconds to update. And then we can see how it deforms. Why does it take so long? No idea. That's the effect of presentation. Okay, sorry. And now we can see the displacement here. Right now, you can just see it here at the border. But we can increase the scale factor, for example, to 10. That means it's 10 times more deformed than it looks like, but it gives us a very good qualitative view of the displacement. And if we no, wait until it's updated, then we can see here, just wait 1 second. And now you can really see here how much the displacement is. So you have a displacement, but I would say it's less than a tenth of a millimeter, so that looks good. And yes, here you can really see it good. This is a gray one is original, how it looks at the beginning, and then the colored one is how the displacement of this arm. Okay, then last part, post-processing. I think I showed you generally what you can do with the post-processor. The best is to play around a little bit with our post-processor. And if you have any questions regarding this, please use the forum. You can do a lot of things like visualizing, displacement, do slices through your material, etc. Okay, great. Thank you very much. And now let's talk about your homework. So in the end, your homework is to redo the simulation I just showed you. For this, we provide you with everything you need. So if you go on this link here on simscale.com/makersworkshop, okay, oh, Maker Workshop, sorry. So here this I think you know, and you can also from now on find a link to the step-by-step instructions. There you can also download the project you need, and also a link to a form you have to use to submit your homework. Yes, and in the end, your job is you will get the CAD model, and your job is to simulate the deformation for the quadcopter arm for 4 different aerodynamical loads like 0.7 Newton, 1.5 Newton, 2.25 Newton, and 3 Newton. Great, guys. Thank you very much for being here. It was very, very nice to host today's session. And right now we have time for your questions. So if you have a question, please write it down and I will try to answer it. So the first question is by Pramod, and he asks, is the theoretical analysis for this done using the concept FEA? And this is absolutely true, Pramod. What we're doing here is finite element analysis, and that is what SimScale, or this is the technology SimScale is using. Guys, are there more questions? Omka wants to know why we select tetrahedral meshing, and that's a good question. Okay. First of all, the reason why we're using this mesher is that this AutoTED mesher is very robust, fast, and easy to parallelize. The reason why we're using tetrahedral meshing or tetrahedral elements is that tetrahedral elements have a lot of advantage when it comes to 3D meshing. What you should just keep in mind, if you have, for example, the circle, and you want to try it to mesh it or to divide it in the end, you want to divide it with the help of hexaeders, it will become a little bit messy. And you will also have the problem of the stairway effect, for example, when doing it with a circle. Or you have to screw your elements. When using a triangle, it's much easier. You can just do it, for example, like that. Which has a much better representation of the surface. And that's the reason why for most or for the most cases it makes sense to use tetrahedral meshing, especially there we have a complex geometry. Krishna wants to know if FEA used only for structural analysis, and what is the engine or the solver for the structural analysis. Okay, Krishna, first of all, maybe let's go back to one of the slides and take a look on the possibilities of SimScale. As I mentioned, you can do a lot of different simulations with SimScale, and for example, this one is a harmonic analysis. So it's a kind of structural analysis which was used for FEA. But you can also do thermostructural analysis, etc. You can also do fluid flow simulations with FEA. But FEA is only strong for structural and thermostructural problems. And we are using different open source solvers. For example, we use for our FE8 tool, we use Codaster and Calculix. Mehmet wants to know, will we retouch models after simulation? I'm not sure what you mean with retouch, but you don't have to modify the model yourself. But for sure, we would love if you modify the model and share with us your insights and your improvements. Manikandans wants to know if it's possible to do multi-physics simulations in SimScale. Yes, it is. Right now, we are supporting CHT. So CHT is a conjugated heat transfer, and then you're simulating the interaction between the fluid flow and structural element. Let's see if we have a good example in our public project. We'll just look for CHT. Oh, I think there was already one. Let's wait until it's loaded and then I can show you a CHT project. Here, for example, this is a heat exchanger simulation. That means you're simulating the flow through a heat exchanger from a fluid perspective, and also the structural heat transfer through the shell of the heat exchanger. Or here we have heat sink electronics cooling. So you're simulating the solid heat transfer within the sink and the fluid heat transfer, the convective heat transfer through the flow. Will there be, is also a question by Chris, will there be more info in the workshop about options, recommendations for defining the model before simulation? Yes, Chris, this is something we will absolutely focus on also during the next session. Mutba asks if we put up mathematical formulas to be used for cross-checking our simulations. Mukta, that's a good point, and it's not very easy every time to validate your simulation just based on some mathematical formulas. We will talk about how to validate the quality of a simulation also during the next sessions. Basically, the first or the most important thing is that all values should be in range, and most of the rest is a lot of experience. Pramod also wants to know if it's possible to do the simulation for the entire quadcopter, even during working, and what if the results would be nearly the same. That's, Pramod, is a good question, and in the end, I think you also give yourself an answer. For sure, it's technically possible to simulate the whole quadcopter. The question is, does it make sense? And from our experience, for sure there will be a slight difference in the structure simulation of the whole quadcopter, including also the effect of the bolts, but in practice the difference is so small that it's really okay to simulate only the arm if you're interested only in the deforming of the arm. Next question is by Ali. How accurate? I want to know how accurate would this analysis be if it was compared to an actual test? What can be done to improve this accuracy? Ali, that's a very good question. First of all, the accuracy of a simulation depends on a lot of different things. Let's say reduce them to 3 points. First point is the model itself. If you want to use a model which cannot consider or is not considering plastic effects, then and you want to simulate something like fatigue, then for sure this is a big problem for your accuracy. So you have first of all to choose the right model and the right assumptions. Then the next step is the mesh. A general rule is the mesh should be as fine as necessary and as coarse as possible. And increasing the mesh size most of the time increase also the accuracy of simulation. What we're looking for in the end is the so-called mesh-independent case. So a mesh which is so fine that any further refinement will not change significantly the results. And last but not least, the choosing the right boundary and conditions is also very important. Krishna asked if we can expect a future FSI workshop series by Simple. Krishna, definitely. We will, as soon FSI is on our list, on our agenda, and it will be available in the near future, and as soon as it's available, we will do a great FSI workshop series. And Pramod also wants to know how we can find out lift and drag forces of the quadcopter. For this, we did just a fluid flow simulation, which we also showed you or teach you during the third session. So we use this fluid flow simulation to get the right forces. Great, guys. I hope I answered all your questions. If not, just ask them right now or ask them in the forum. I will send the email to you latest by tomorrow, where you can find all resources, and I'm really looking forward to next week, to our next session. Okay, just a question by Alex. Alex say he's just wondering the numerical values I give for any simulation. Do you follow any parameters? Alex, can you maybe specify your question a little bit more? I'm not sure what you really want to know. So are you talking in general about where I get the boundary conditions, or are you talking more about the numerical settings? Okay, boundary conditions. Okay, well, for example, maybe let's go back to the simulation itself. Here. For example, in the end, I can only give boundary conditions to those areas where I know what will happen. I know that this and this face cannot move because I'm looking at the relative, let's say, it should be fixed here, so it cannot move. And therefore, X displacement, Y displacement, Z displacement can be prescribed with 0. And for the load, as I mentioned, I just simulated the load generated by the propeller on this drone for the whole drone, divided it by 4, and added it on this face because it must be normal to this face. Great, Alex. I hope this answered your questions. Most of what you'll also learn in the next weeks, how to you will learn also next week how to develop your own boundary conditions. Okay, then thank you very much for your time, guys. If you have more questions, just write into the forum. And I'm really looking forward to the next week. Let's rock it. Happy simulation to every of you, and see you next week. Bye.